In this video, we're going to talk about how to solve trigonometric equations for the set of all values. And the assumption is you watched the first video on how to solve a trigonometric equation just for values between 0 and 2 pi or 0 and 360. So the idea here is that once you get the set of values by solving and using the inverse function, that these values actually have more answers than you're seeing because of the fact that these continue to occur using the unit circle. So if I think about this answer on the unit circle, what ends up happening is the unit circle has this value here at pi over 3, okay? But anytime I land on this, I would also have a solution to this equation. So for instance, pi over 3 is here, but if I come all the way back around to here, I would have another answer. And we can think up what that answer actually is, but every time this happens, it would happen. So if I came here and then came around twice, it would have an answer. I could also go backwards and go this way, and it would have an answer. So the way we describe that, if we go all the way around the circle, that would be 2 pi. And if we talk about the idea that we're going backwards and forwards, that would be plus or minus 2 pi. So one way to think about this is to take this answer and add plus or minus 2 pi to it. But there's an easier way to think about it if we just said, because this is just saying once, this would just say pi over 3 plus 2 pi or pi over 3 minus 2 pi. And that would only give us 3 answers, but there's actually an infinite amount of answers. And so the best way to describe that would just simply put a z in here, meaning integers, meaning you would take pi over 3, and then you would add 2 z pi, meaning 2 times any integer and pi. Some people might say 2 pi z. I like to put the z in there like that. So what that is that's a sequence. That's the same thing as when you learned about an equals a1 plus n minus 1 times d. And if you actually ran through that formula, it would be a little different than what I have here. But what this does is this gives you a visual way to see it, and this is in fact a sequence. This is the algebraic way to write the sequence, and it will come out with a slightly different looking answer that's actually mathematically equivalent. So I think the easiest way to do it is think about sequences visually here and not think about them so algebraically. Now that's just one of the answers. That's this answer written out as an infinite answer. But if I were to take this one, there's no connection between these two. So I'd have to think about that one as well. That one's 2/3. So if I take this 2 pi over 3 and I put it there, again, it's not going to become the answer again until we go 2 pi or 2 pi again or 2 pi again, or if we go backwards. So these two answers written out as infinite solutions are pi over 3 plus 2z pi. You might say, why don't you have a plus or minus? The reason is because the integer is plus or minus, so I don't need to worry about it. Remember, integer is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but also 0, negative 1, 2, 3, 4, 5, 6, 7. So I don't need the plus or minus. And then here, since this one has the same idea, we would have 2 pi over 3 plus 2z pi as well. For this one, nothing really new here, so same idea, right? So because 2/3, again, it's actually the same as this, and then 4/3 would be right below it. But when we look at this third one, something very interesting happens. So we worked through the problem, we took a square root, so we had a plus or minus right here, and then we had the inverse tangent plus or minus 1, which gave us every pi over 4 or every 45 degree. This one was in degrees, so I did it with degrees. I'll show you both in this example. So what ends up happening is this actually has a connection to itself. So I'll show you what I mean by that. If I look at this answer right here, and I draw the unit circle representing this, and again, this is just a visual sequence, and we can show the algebraic sequence as well. The first one's at 45, okay? The next one is at 135. The next one is at 225. The next one is at 315, and then I would be back to here. So if I were to go around the unit circle, I would start to engage these every 90 degrees, right? Because how far apart is 45 degrees from 135? Okay, so this is when that idea of sequences really is important. Like if I were to write this out as a sequence, this differs from this by 90 degrees. This is your D in your sequence equation. And then this is also 90. This is also 90. So this is where knowing this formula right here can really be helpful. If you would rather, in this problem, write 45 plus n minus 1 times 90 and simplify it, you will get an answer, and it might make more sense to do it that way. It might be slightly different than the visual sequence. So down here, again, this is still 90, this is still 90, this is still 90. So to do this visually, we started at 45, and we're adding 90 degrees times the integer values. This would also be the same thing if I went backwards. So if you were thinking, well, what about, Mr. King, the fact that if you have coterminal versions going this way? Now, the thing about that is, right, the thing about that is that the z has the plus or minus built in. Don't need to put it here. It would be redundant. I don't know that most teachers would count it wrong, but it is redundant. So 45 plus 90z, if I want it to work out this equation where I said an is equal to a1, so a1 would be 45 plus n minus 1 times d, where d was 90, I again would get a similar equation, but it would be a little different because of this. Okay, and that's something, you know, that we can talk about later when we talk more about sequences of series on a higher level understanding, that sequences of series do have an equation that you can write using this formula, but sometimes there's more than one way to write that formula. You know, when you first learn sequences of series, we give you a formula that relates to algebraic concepts. But this formula right here will provide the answer as well. And keep in mind, if we did this in radians, I know that the assignment in this case was to go to degrees. The radian version would be pi over 4, because that is the same thing as 45 degrees. And then we would want to add in any 90 degrees. So in the world of radians, that's pi over 2. And then we want to put a z there. So to show you that this works really well, and it does actually make sense, and it is the correct sequence, watch what happens if I were to type this in the calculator. So if I go into my mode, I currently have it in radian mode. I'm going to go to degree mode. So if I put this in degree mode, and I type in the original equation, which is tangent squared x equals 1. So I'm going to, in a normal calculator, you typically have to surround the function with a parentheses to square it. So I'm going to put in the first answer we got, 45, and then I'm going to square it, and the answer will say 1, because that's what the equation says. So this right here matches that. But watch what happens when I put this in. So if I go in here and I say, hey, I want to put in tangent, but I'm actually going to put in the formula we came up with. You can put it right in here. Okay, so plus 90 degrees times z. So I can put in plus 90, and it's going to work. Okay, see, equals 1. I can put anything in here that's an integer. So if I go in here and put 90, I have to multiply it, because remember, z is being multiplied. And if I multiply times any integer you want, we'll make it a crazy integer. We'll make it negative 1236. Just randomly made that up. It's still going to come out to 1, because that's what our formula says it will do. Same thing with radians. I just have to change the calculator back to radian mode. So let's take a look at our more complicated ones we solved in the previous video. So these involved algebra 2 concepts from quadratics. It involved taking square roots, and it involved factoring by greatest common factor, and it involved factoring using whatever technique you do to separate out a quadratic equation. So let's take a look at these answers. So when you look at this answer right here, okay, what ends up happening is you have 30 degrees, and it doesn't align with 150, as you can see here, because 150 is over there. 30 degrees actually aligns with 210. So 30, right, aligns with 210, and every single time you have a line on the unit circle, that is going to be always 180 degrees. We learned that in geometry, that lines are 180 degrees. So how far apart are these two answers? They're 180 degrees apart. So the first answer is 30 plus 180 degrees times z. Now you might say, where'd the 210 go? Well, 30 plus 180 is 210. So in the infinite answer, in the answer over all solutions, I don't need to include 210 because it's actually already right here. Again, I don't need the plus or minus because that's in the z. So to take a look at the second sequence that represents the answer, if I take 150 and I look at 330, they are also separated again by 180 degrees. So the other answer is to make this your A1. So your second sequence, this is A1. So 150 plus the separation of 180 degrees times any multiple of z. So this is your first a1, right? So that's this equation. And this is your second a1, so that's this equation. And either one of them will work. So to check this with a calculator, it might be a good idea to not use your typical calculator because the amount of parentheses required to put this in, it gets complicated. So I'm going to use an online calculator from Desmos. And you can see what I did is, if I type in here 180, which is the answer, 30 plus 180, it gives me the answer of 2. So again, I typed in 3 tangent squared x plus 1 equals 2. And the nice thing about a program like Desmos is you can actually put that square there where you cannot do that on a calculator. So I can change this to any integer, and that's what's beautiful about it. If you want to put 0 in there, that's one of the integers, it's still 2. If you want to put 1 in there, still 2. Negative 1, still 2. Negative 34, still 2. I could put positive 123,789, it's still equal to 2. No matter what I do, I'm getting the same thing, which is what solving an equation is, okay? So again, to type that in the calculator, it would have a lot of parentheses. It would have to have a parentheses here, then a tangent, then you'd have to put inside of x what your answer is, so 30 plus 180, and then you can put z's in there. Then you'd have to close it, then square the whole thing, and then add 1, and it will come out to 2. So it's a little bit more complicated, but it still works. And that's how any calculators would be as long as you had it in the right mode. So let's take a look at the next one. Each one of these has an interesting way to write things in infinite solutions. So when I solved this one, remember I GCF'd it, and then I solved it. I solved each of these parts separately using the zero product property from Algebra 2. And I figured out where cosine was equal to 0, and I figured out where cosine was equal to 1. In this equation, we exclude that value because it doesn't have an equal sign. It's a little tricky thing that people like to do in trig to make sure you're paying attention. But for infinite solutions, we really would want to think about that as an answer. And the reason we want to think about it, again, for the defined interval, it doesn't have an equal. It's kind of sneaky. But in the infinites, on all values, that obviously would be an answer because equal versus not equal doesn't matter on an infinite plane. So if I think about this first answer, these two things are connected, again, by a separation of 180 degrees, right? So the first one's here at 0, and then 360 degrees back around, I have 2 pi. So these are separated by 360. So one way to write it would be 0 plus, right, 360, right? But we're talking about pi, so 360 degrees. But since we're talking about pi's in this case, we would change the 360 to 2 pi. So we would say 2 pi. And then we put a z in there. But I think you understand if a1 is 0, it's not really significant. So the answer would just be this, every single 2 pi, otherwise known as 2z pi. So that's the first answer. The second answer, which is how these are separated by also, if you look here, we start at pi over 2. And then if we go to the next answer is 3 pi over 2. And then the next answer would be to come back to pi over 2, and then 3 pi over 2. So we just keep going around in a cycle that way. And those are separated by 180 degrees. But since we're talking about radians, they're separated by pi. So if your A1 is this, and your D is pi, it would be pi over 2 plus z pi. So just to show you again on Desmos, which I think is a great way to write these in, especially when you think about how you have to put in the square. You write in cosine, you put in your parentheses. To put the square in, you just click right there and put your square in, okay? And so our first answer, so we have cosine squared minus cosine doesn't equal 0. I'm going to put in the more complicated one. I'm going to put pi over 2 plus z pi in. So when I do that, I'm going to go in here, I'm going to put pi over 2. You can actually type in pi, or you can use this and use the backslash, and it'll turn into a fraction. And then we were adding to that one, we were adding pi to that one, so we'll put pi back in there. Oops, forgot to put the plus, so plus pi. And then we also want to add cosine to that, and we actually have to put the exact same thing in, because when you have two x's, when you look at the equation, there are two x's, which means you have to substitute the answer in 2 times. So again, I'm putting in just this one to start. So I can actually, the nice thing about Desmos, I can just copy this. I can just Control-C, Control-V, put it in there. Okay, now why does that not come out to what it says? It says it should come out to 0. And the reason it's not coming out to it, if you're astute, is it's on degree mode. So if you put it in radian mode, it comes out to the right answer. Again, this is thinking it's degrees. You know, putting a pi in as a degree is like a logical mismatch. But when I put it back in radian mode, we have the right answer. And again, any integer value. So if I put a 4 here, I have to put it here, still have 0. If I don't put the 4 there, obviously, it's, you know, we might have a problem. So I can put anything I want in there. I could put negative 98, and then here I can put negative 98, and it will come out to 0. So we have found that infinite answer we were after. Same thing would work with 2 pi. So if I go in there and just put in any version of 2 pi, and again, the nice thing about using an online calculator like Desmos is that you can just copy. You see that we get what we're supposed to get. So let's take a look at this last one. So the last one we factored out, right? We factored out what we needed, and what we have there is we have a equation that maybe it makes more sense to write this out as s squared plus 2s, s being sine minus 3, and then I think most people could factor that out very easily as s plus 3, right, and then s minus 1, because, you know, many people, there's lots of ways to factor, but 3 minus 1 is 2, and 3 times negative 1 is negative 3. And then you do the zero product property. You find this has no solution because it's not in the domain. If you think about the unit circle, all the values around the unit circle, they're always going to be between negative 1 and 1. So asking what 3 is on the unit circle makes no sense. And then we just have this last answer that is 90 degrees. And so 90 degrees is really easy to come up with an equation for, because if we start at 90 degrees right here, then what's going to happen is we're not going to get the answer until we come all the way around, or all the way around again, or going backwards. So that one's pretty easy to do because going all the way around is 360. So I'll show you that last one on here. Let's take a look at it. What I would have is I would have the equation, which is 3. Make sure I have it right in my brain. It's sine squared plus 2 sine x equals 3. So sine squared, right? And then our first answer was 90, so I'll put it in there. And then plus 2 sine 90. And the question is, does it equal 3? It doesn't because it's in radian mode, but when I put it in degree mode, it does. And then any integer version of this. So I could put in times 3, like this, right? No matter what. Oh, I messed up. It wasn't, I'm putting in the wrong equation because remember, we had to add 360. So let's put that back in there. Just be careful what you're typing. Make sure that what you're typing represents your formula. So if we add any integer value of 360, now we'll have the right answer of 3. And where does 3 come from? It says 3 here. So now that you're seeing that what we're coming up with, and again, if I say, okay, multiply that times any integer value, so I'll say times 67, right? That's an integer. So times 67. You can still, oops, I put 68. You can see that it still equals 3. So just to, you know, I hope that helps you understand how there can be more than just the answers on the unit circle. Like these answers are great if you're trying to find just the unit circle answers, but hopefully showing you how these formulas work help you understand that there's an infinite amount of answers. And though we can use the formula an equals a1 plus n minus 1 times d, which you learned about in Algebra 2, okay, though we learned that formula, right, sometimes comes out slightly different. And it's an important thing to understand that this formula is algebraic, but these answers we're getting are visual. They're a picture understanding of what's happening, and they are mathematically equivalent to the algebraic version. Well, I hope you enjoyed this video, and I hope it helped you understand how answers can be more than just what you see. They can be more broad.